Hello there, Mr. Sutton here, bringing you the AB Calculus 512 classwork solutions on FTC free response practice. For this free response problem, g is this piecewise linear function given up here, and we have this f function that's going to be g of x minus cosine of x over 2. For the first task on this, we want to find just the integral from negative 2 pi to 4 pi of f of x. Okay, well, since f of x is made up of these two other functions, the integral of f of x is essentially the integral of g of x minus the integral of cosine of x over 2. So we can split it up like this. And next, let's see here, integral of g of x from negative 2 pi to 4 pi. Well, we don't have a function really for g of x algebraic, but we do have a graph, so we can just find the area under the g function in this graph. This is just one big triangle. So we're going to have 1/2 times a base of, let's see here, this is 6 pi times a height of 2 pi. And then for the integral from negative 2 pi to 4 pi of cosine of x over 2, well, this we can use our FTC and take the antiderivative and plug in our limits of integration. So antiderivative of cosine is going to be sine, but we have an interlinear function here, so we have to divide by the derivative of this. Dividing by 1/2, we're really multiplying by 2. So when the dust settles, we have a little evaluation box, and we're going to be subtracting 2 sine of x over 2, evaluated from negative 2 pi to 4 pi. All right, let's clean this up a little bit. So this stuff out in front, we can multiply this out. This is going to be, let's see here, 3 pi times 2 pi, which is 6 pi squared. And then for our evaluation box, I'm going to pull out a 2, and in the parentheses next to this, I'm going to have sine of 4 pi over 2 minus sine of negative 2 pi over 2. Well, let's see here. We've got 6 pi squared again. There's nothing that's really going to get combined with that. And let's see, sine of 4 pi over 2. Well, that's really sine of 2 pi, which is 0. Over here, we have sine of negative pi, which is also 0. So this whole bracket's parentheses here is just 0. So 2 is going to get zeroed out then, and 6 pi squared is our final answer. On this part of the problem, we want to find all x values in the interval from negative 2 pi to 4 pi, for which f, which again they defined up here, has a critical point. So basically we're asking at what x values is f prime either 0 or undefined. Let's do the 0 part of it first. What is f prime even algebraically? If we take f prime, we're really taking the prime of both of these functions individually. So f prime is going to be equal to g prime, and then this is going to be plus 1/2 sine of x over 2, just using a little chain rule there. Okay, well, we want to know where this equals 0 or is undefined, either of those things. But let's start with 0. So to figure out where this is 0, that's going to be a little tricky because we don't know what g prime is algebraically. But the good news is we have a graph of g, and this graph is just 2 lines. So we can actually talk about g prime on different intervals. For example, on the interval from negative 2 pi to 0, g prime, which is just the slope of our g graph, is just going to be 1. This is just a slope of 1 here. So we can write this equation as 1 plus 1/2 sine of x over 2 equals 0. And then if we subtract 1 and multiply by 2, we have sine of x over 2 equals negative 2. But there's just one problem. Sine can never equal negative 2, or really anything that's less than negative 1 or greater than positive 1. So because sine of whatever can't equal negative 2, this is just a dead end here. So we are going to also consider now the interval from 0 to 4 pi, where g prime has a completely different value. On this interval, g prime has a value of, let's see here, we're going down 1 over 2 essentially. So granted this scale is in pies, but it's down 1 pi over 2 pi. So that's still a slope of negative 1/2. So we can write negative 1/2 plus 1/2 sine of x over 2 equals 0. And if I add 1/2 to the other side, I can cancel out the 1/2s. So I just end up with sine of x over 2 equals 1. Taking the inverse sine of both sides, well, let's see here. Where does sine equal 1? That's going to be where your angle is going straight up, so pi over 2. And in terms of the interval here, I mean, there's more than one place where sine equals 1. We've got pi over 2. We've also got, let's see here, 5 pi over 2, and like every 2 pi, you're at that spot, you're getting another sine value of 1. But in terms of things that are actually going to fall in this interval when we multiply them by 2, pi over 2, I believe, is the only one. So x over 2 is going to equal pi over 2 then. So multiplying both sides by 2, we have x equals pi, and that's giving us one critical value. This is one value, at least between negative 2 pi and 4 pi, that is going to give you 0 when you plug it in this derivative. So that's all the values that we could possibly get by having f prime equals 0. However, we also have to consider where f prime is undefined. And sine is not undefined anywhere, so we're not going to have issues there. But g prime is not going to be defined everywhere. Because if you look at the graph of g, there is a non-differentiable spot. Right here at 0, g has a corner where you can't take the derivative. Since g prime does not exist at that corner, that means f prime does not exist at that corner. So you also have a critical value then at 0, as well as pi, because f prime does not exist at 0. For this last problem part on this one, we're letting the h function, newly defined here, be the integral from 0 to 3x of g of t dt. Based off of this, we just want to find h prime of negative pi over 3. So since we're taking the derivative of this integral that has a variable in the upper limit, we're going to be using our fundamental theorem of calculus. Basically, we're going to plug in this upper limit for the dummy variable, and then if there's a chain rule to be applied, we'll do it. So we're going to have h prime of x equaling g of 3x times, because 3x has a derivative that's not just 1, times a tail of 3, the derivative of 3x. So we're using the chain rule there. All right, at this point, we just have to plug negative pi over 3 into this. So this is going to be g of 3 times negative pi over 3, all of that times a 3. I'll put that 3 out front there. Well, inside the g function, these 3's are going to cancel. So this is 3g of negative pi. And g of negative pi, we can definitely look that up because we have the graph of g right here. So remember, these grid lines are all going by pi's. So negative pi is right here. Looking that up on the g function, that appears to be positive 1 pi. So we have 3 times 1 pi, or just 3 pi. On this free response problem, we have the functions f and g, which have continuous second derivatives, which means basically you're twice differentiable on those. And we have a table here giving us values of f, g, and their derivatives at certain places. For our first task here, we want k of x to equal f of g of x, and we're just going to write an equation now for the tangent line for k at x equals 3. So in general, we're going to use point slope here. Y minus y1 equals m times x minus x1. You don't get anything for writing this in particular, but I like to have kind of a place to plug things into. So y1 in this case, since we're finding a tangent line for k, y1 is going to be f of g of 3, because that's the x value we're plugging in. M is going to be the derivative of k at x equals 3. For that, we're going to need a chain rule, which in general would be f prime of g times g prime of x. So this is going to be f prime of g of 3 times g prime of 3. So this whole thing is going to be our slope when we figure out what it is. And then we have the x minus 3 in the parentheses there. Okay, let's clean this up a little bit. So g of 3, let me look that up in the table. So the x value 3, plugging in that to g, we get 6 back. So this is going to be f of 6 right here. And over here, this is going to be f prime of 6. And then we have the rest of this stuff here. Let's next find what f of 6 is. So let's see here. That's going to be 4. So we have y minus 4 out here. F prime of 6 we'll also look up. F prime of 6 is going to be 5. So this equals 5 times g prime of 3. Well, g prime of 3, looking that up, looks like that's going to be 2. And then we have x minus 3 right after that. So this is all constants. You could leave it like this, or you can write y minus 4 equals 10, parentheses x minus 3, and that would also work. For this problem part, we're defining h of x as g of x over f of x, and we want h prime of 1. So we basically need to use the quotient rule here, u prime v minus uv prime over v squared. That's what h prime of x is going to be in general. So let me set up a box and ribbon to help me with this. So I've got my numerator, g of x, I'll put that right here. Denominator, f of x. So we've got a u and a v. Now we need a u prime and a v prime. Derivatives of these things, which conveniently are just g prime and f prime. So before I actually throw all this together and plug in 1, I am going to plug 1 in the table, in the box here. So let me make another box where if x equals 1, here what all these things actually equal. Then I'll put it back together over here using this basic structure. So if x is 1, what's g of x? Well, g of 1, looking that up in the table, g of 1 is going to be 2. And then f of 1 is going to be negative 6. G prime of 1, looking that up, that is going to be 8. And then finally, f prime of 1, that's going to be 3. So using the ribbon to put all this back together, we have 8 times negative 6. So this is what h prime of 1 is going to equal, minus 2 times 3. This is the uv prime part, all over negative 6 squared. That's the v squared part of this. Simplifying this a little bit, this is going to be negative 48 minus 6, which is negative 54. We have a positive 36 on the bottom. And if you wanted to reduce this, not sure why you need to, but if you did, these are both divisible by 9. So let's see here. This is going to be, and actually we could probably go a little bit further than that, but let me see here. Actually 18. These are both divisible by 18. So dividing by 18 on the top and the bottom, we've got negative 3 halves when all is said and done. For this problem part, we want the integral from 1 to 3 of f double prime of 2x dx. So we're going to use our fundamental theorem and basically take the antiderivative of this thing and then plug in 1 and 3 and subtract. So antiderivative of f double prime in general would just be f prime, but since you have this interlinear function, you have to divide by the tail here. So this ends up being 1/2 f prime of 2x, evaluated from 1 to 3. So I'm going to yank the 1/2 out of here, and we're going to have inside, I'm going to have f prime of 2 times 3 minus f prime of 2 times 1. Well, what is f prime of 2 times 3? That's really f prime of 6. F prime of 6 is going to be 5. And then this is really just f prime of 2 over here. F prime of 2, that's going to be negative 2, but we're subtracting that, so that's actually plus 2. So we've got 1/2 times 7, which comes out to 7/2. For this calculator-based free response problem, we have a g function defined for positive numbers. G of 1 they told us was 2, and not a whole lot else about g. But here's g prime, and here's g double prime. Based off of this, we want to find all x values between 0.12 and 1, which is kind of a weird interval here, at which the graph of g has a horizontal tangent line. Well, we basically are asking where is g prime equal to 0. That's what happens if you have a horizontal tangent line, you have a slope of 0. So g prime of x, which they've already defined for us, so we don't have to rewrite it, equals 0, and this is where we look this up on the calculator now. So here I am on my calculator in my y equals. y1 is going to be this g prime function right here. I'm going to go ahead and graph it, but before I do that, let me set my window. I'm going to make my window 0.12 to 1, just so I can match what they said in the problem was the domain of this function. And then let me do zoom 0, zoom fit. And we're basically going to look to see where this crosses the x-axis. Now it looks like we're crossing 2 times, once here and once over here. Let's figure out what those 2 spots are. So doing second trace, zeros, option 2. I'm going to move my spider to be a little bit to the left of that first crossing. Whee! There we go. Whoop. We'll go back a little bit. All right. So press enter. Move it a little bit to the right. Press enter again. Enter a third time. And that comes out to about 0.163. So there was our graph. There was our first intersection. And then let's go back and find the other one now. So let me do second trace, option 2 again. And moving forward a little bit, we have to click a little bit to the left of this x-intercept. There we go. And a little bit to the right. Press enter again. A third enter gives us 0.359. So those are the two x values at which we have horizontal tangent lines because g prime is 0 there. For this problem part here, we want to know on what interval between 0.12 and 1 is the graph of g concave down. Justify our answer. Well, concave down, we're talking about where g double prime is negative. And since we have the function for g double prime, let's graph this out and see what we're dealing with. Now, to figure out where g double prime is negative, it would help to at least know where g double prime equals 0. That'll give me some numbers that I can write some intervals with. So let me go on my calculator again. So here I am back in my y equals, and you'll see here in y2 I've entered this even crazier g double prime function. I'm going to graph that in a sec, but let me deselect y1 because I don't want to graph the g prime again, just g double prime. And for my window, let's see here, I'm going from 0.12 to 1 still, so that's good. All right, let me zoom 0 this thing and see what happens. So this will probably take a little bit longer to graph, but not too much longer. So it looks like, are we crossing there? It's kind of hard to tell. Kind of hard to tell if we're crossing over there. But at the very least, let's take a look at these two intercepts and see what they are, and then maybe we'll zoom in a little bit on this and see what we can see. So we've got, let's see here, second trace, option 0, or option 2 again for zeros. And let's see here, this is going to be kind of tough to position my spider, so I'm actually going to enter a value over here. I'm going to enter the value 0.12 for my left bound because that's as far left as I'm allowed to go. And for my right bound, let me just see if I can move my spider a little bit. There it is. Press enter again, and we've got the spot 0.129, very, very close to the y-axis there, but it counts. So there's one spot right there. And then let me get another spot. This spot right here, also pretty easy to pick out. So let's see, second trace, options 2, left bound, move up a little bit. There we go. And press enter after I go to the right. There we go again. Enter again. And this one is about 0.223. Are there any more spots over there? Well, we can explore this. So let me just trace my function and let me just take a look and see if my y value ever dips below 0. So there we go. We're moving. And we're getting closer and closer and closer to 0. Do we ever get below 0? Not until we get to x equals 1. So I think we can conclude here that we're not getting negative anywhere in there. All right. So what we wanted to know is where the graph was concave down. So we're basically asking where's g double prime less than 0, negative. And that's going to be between 0.129 and 0.223, which we now know what these x values are here, and we can observe from the graph that g double prime is negative between those points. So in terms of justifying my answer then, g double prime is less than 0 on this interval here, between 0.129 and 0.223. Therefore, g is concave down on this interval. On this part of the problem, they want the equation for the tangent line for the graph of g at x equals 0.3. So in general, we're going to use point slope, y minus y1 equals m times x minus x1. We don't get anything for writing this, but it at least tells me what I'm looking for and where to plug it in. For y1, this is the y value when x equals 0.3. This is the y value for the g function. So I don't know how to get that just yet because they only gave me g of 1 here, but let's put it in here. This is supposed to be g of 0.3. So we'll figure that out in a minute. For this next thing, m, that's the derivative of the g function at 0.03, or 0.3 rather. So this is going to be g prime of 0.3. And I'll have to use the calculator to find that. And then finally, we have x minus the x value, 0.3. That's like the only thing we can put an actual number in for here. All right, so let's get each of these. And I'm just going to get decimals rounded if needed out to 3 decimal places. So for g of 0.3, I know that g of 1 is 2. And I have the rate of change of g. So I can actually use my fundamental theorem to figure out g of any value I want using these two facts. So I can say g of 0.3 is going to be equal to this value here of 2 plus the integral from 1, which is the value we have here, to 0.3 of g prime of x dx. This I'm going to have to do on the calculator. So here's what this looks like on my calculator. I have 2 plus integral, which was math 9, from 1 to 0.3. I did alpha trace to pull up the y menu, and I put y1 in there because that's where I stored g prime. And this is an x out here, dx. Pressing enter, that's about 1.546. I'll just round it off to 3 decimals there. So that's what's going to go in for g of 0.3 in a moment. But next, I need to figure out g prime of 0.3. Now, since I already have the g prime function right there, I just need to plug 0.3 into this function. Let me go back to my calculator now. So let me just do alpha trace y1, and I'll just open a parentheses and plug 0.3 into this directly. And press enter. That's about negative 0.472. So there's that piece of it. I'm putting it all together now. We can write y minus the y value 1.546 equals the slope I just found here of negative 0.472 times x minus 0.3. For this last part of the problem, they want to know if the tangent line to the graph at 0.3 lies above or below the graph of g on the interval from 0.3 to 1, and then why. So whether or not your tangent line is over or under a graph, this is all about the concavity of the graph. What is the concavity of g on this interval? Well, we found in part B that our graph was concave down on the interval from 0.129 to 0.223. That means that outside this interval, everywhere else, it's concave up. Specifically, we know that our graph is going to be concave up on the interval from 0.3 to 1, because that interval falls after this interval on our graph. So what this tells us, since we are concave up on the interval in question here, our tangent line is going to be underneath the curve. This is just known that your tangent line is going to be below if your function is concave up. Because if you think about it, concave up, that's like an upward facing parabola, and then your line always has to fall under it if you're hitting it in just one spot. So there we go.